Okay, we're starting chapter 9, which is on hypothesis testing. And this is the last chapter we'll cover for Business Stat 1. Business Stat 2 will start with hypothesis testing, so we will get a double dose of this topic. But let's just recall that our goal here has been statistical inference, right? Statistical inference on a population mean and a proportion pi. So we're interested in these population parameters. We take a sample, we get these point estimates, right? So if we're interested in the population mean, then we will get a point estimate of the sample mean x bar. If we are interested in the population proportion pi, we will get a point estimate from our sample and call it p. Okay, that was, I think, chapter 7. I don't even remember. Yeah, on sampling distributions. But then we moved on to chapter 8, where we weren't just interested in this one point. So instead, we generated a confidence interval around these sample statistics. So we got these point estimates, and then we added some and we subtracted some, and we called this a confidence interval. And this established a range of plausible values for the population parameters. So recall, we had just like this one point, we call it, say, x bar. But then we created an interval around x bar. So this is x bar plus margin of error. And then we had x bar minus margin of error. And that was the last chapter. But now we want to perform formal tests on our sample to answer research questions about the population parameters. So let me just clean this up a little. So we want to perform these formal tests on our sample to answer research questions about the population parameters. And we're going to call this process hypothesis testing. So we're going to take a sample, and then using that sample, we calculate our point estimate, x bar. And then we're going to formulate a question around that. Do we have enough evidence to say that the mean is truly greater than some value or truly less than some value? And that's what we're formally testing here. So our hypothesis will be whether the average is greater than, less than, not equal to some hypothesized value. And this whole process is called hypothesis testing. So we're going to use a 5-step process. So I think if you look in the PowerPoint, it's a 6-step process. It doesn't really matter. Let's just go with 5. We're doing the same thing. I just think this is the most convenient way to go about this. So the first step is to formulate our hypotheses, which are really just our research questions of interest. So starting with the null hypothesis. So the null hypothesis we're going to represent as H naught, null hypothesis. And this is what we call the status quo, or I like to think of it more as a statement of equality. So what we're ultimately doing is that we assume that the null hypothesis is true. So we're going to assume H naught is true. But then the goal of this hypothesis test is to try to prove it false. So I think if you look in the PowerPoint, H naught is that we are innocent. And so, if someone is convicted of something, we say that they are innocent until proven guilty. So we're going to assume innocence and then see if we can prove that false and determine that they are actually guilty. So then we need to discuss the alternative hypothesis. So the alternative hypothesis will represent with HA. You might also see it written as H1 instead. So the alternative hypothesis is the actual research question here regarding some hypothesized value. So it's our actual research question. So it's going to be the complement. So remember, complement, or sorry, I should finish my sentence. The complement of the null hypothesis. So the complement, recall, is just the opposite of something. So if H naught is innocent, then HA is guilty. So the alternative hypothesis is the complement of the null hypothesis. And what we're trying to do is that if we can determine that the null hypothesis is false, then we will accept the alternative hypothesis to be true. So we're assuming someone to be innocent, and we're trying to show that they are truly guilty, in which case we would reject innocence and accept that they are guilty. So our hypotheses will take on a couple of different forms. And the first is what we call a two-sided test. So we are saying that the true population mean is equal to some hypothesized value h naught or mu naught. So mu naught is the hypothesized value. So in this case, we're saying it's two-sided because what we're assuming to be true is that the average is just equal to some value. So what we're testing then is to see if it's actually different from that value. So different could be less than that value or greater than that value. And so because we're interested in both sides, that's why we're calling it a two-sided test. By contrast, our one-sided test would look something like this, where we're assuming the mean to be less than or equal to some value. And so I have these backwards. I apologize. Okay, we're assuming the mean to be less than or equal to some value. And so we're going to test whether the mean is bigger than that value. And over here, we're assuming the mean to be greater than or equal to mu naught. And so what we're going to test is to see whether mu is less than that value. So in this case, we're only interested in one side of mu naught, the hypothesized value. Okay. So let's do an example. So it's suggested, I just Googled this, and Google said that the average male height in the US is 5'9", which is about 69.1 inches. So can we conclude whether the average male height is actually 69.1? So let's write H naught and HA. So notice that the wording here is not less than or greater than, and we're just trying to determine whether the true average is equal to 69.1 or not. So mu naught here, the hypothesized value, 69.1. So we're saying the mu is equal to 69.1, and we want to test if this is actually not the case. So we're going to say mu not equal to 69.1. And so this is going to be a two-sided test because we assume that the average is 69.1. We want to test if that's true. So that means it could be less than that value or it could be greater than that value. And so therefore it's a two-sided test. Okay, let's do another example. Americans work 40 hours per week. And let's say we want to test whether Europeans work less than the typical American on average. So let's call mu the average number of weekly work hours by Europeans. Okay, so we want to see, do Europeans work less than Americans? So let's first note that mu naught here will be 40 hours. Okay, H naught and HA. So we want to know if Europeans work less than Americans. So Americans work 40 hours, then that means we're testing whether mu is less than 40. Notice that less than is coming from Europeans work less than Americans. And so because the null and alternative hypothesis, these are complements of one another, then that means our null hypothesis is mu is greater than or equal to 40 hours. And so this is going to be a one-sided test. Because here it is less than. And so if we have a less than or a greater than here, we call it one-sided, compared to up here where not equal to is what we call a two-sided test. Okay, so that's step one. Now let's talk about step two. So step two, we want to calculate a test statistic. Okay, so we already know that we collect our sample, and we're going to use that sample of data to calculate our point estimates of x bar and s. Or if we're talking about proportion, that would be p. So then we're going to calculate our test statistic. So test statistic, t-stat, where t-stat is equal to this formula. Recall, this is the same formula we were using in the prior chapter. So it's very similar to a z-score formula. It's just slightly different because we're now calling it t, or in this case, t-stat. So same formula as chapter 8. And so if you recall, our interpretation of what this number means, it's the number of standard deviations x bar is above or below our hypothesized value, mu naught. So we're seeing we have this hypothesized value from the question of interest, and we're seeing how far away x bar is from that value, and the t-statistic is going to tell us how many standard deviations away x bar is away from mu naught. So we need to make a couple assumptions for the t-statistic. So one is that we need to assume that our sample is a random sample. And the second is that the population is normally distributed. Alternatively, we could say our sample is large enough, so n bigger than or equal to 30, and that way we can rely on our friend, the central limit theorem. Okay, we need to make a quick definition. So alpha. Alpha is what we're going to call the significance level. Alpha is the probability of rejecting H naught when in fact H naught is true. So in that case, it's an error. H naught was true, but we said it was false. And we're going to call this a type 1 error. So as researchers, we're actually going to choose alpha before we perform any hypothesis test. So if we're scientists or researchers, whatever, we need to choose this before we start performing any statistical test. We're just saying alpha is the level or the amount of time we are willing to be incorrect, and we get to decide how often that is. Alternatively, or I shouldn't say, similarly, a type 2 error is the probability of not rejecting H naught when H naught in fact should have been rejected. But we're only going to control our type 1 error. We're not going to focus too much on type 2 errors, so let's just focus for now on type 1, which is what, and we're going to refer to it as alpha. Okay, step 3. So step 3. We want to establish a rejection region. So this is going to be based on our significance level alpha. We're going to determine how far away from 0. So we need to determine how far away from 0 t-stat needs to be. I should say, we need to determine how far away. Okay, sorry, let me restart that sentence. Okay, what we're doing is we're trying to determine how far away t-stat needs to be away from 0 in order to reject H naught. So we're going to refer to t-stat. We're interested in extreme values of t-stat. What I mean by extreme values are just values far away from 0. So that could be large positive values, or that could be large negative values. Okay, and the rejection region is going to determine that threshold value that t-stat needs to pass in order to reject the null hypothesis. And this rejection region is going to follow from the alternative hypothesis. Okay, and there's just this one-to-one correspondence, which is if we have a two-sided test, so that's alternative hypothesis is mu not equal to mu naught, then our rejection region is going to be t stat less than negative Tn minus 1 alpha over 2, or t stat greater than Tn minus 1 alpha over 2. So notice that we're using alpha over 2 because with a two-sided test, we're interested in mean greater than mu naught or mu less than mu naught. And so we could be wrong in either direction. Therefore, we need to create two different ranges for the rejection region. But let's say we were doing a one-sided test. So say mu less than mu naught. Well, then the rejection region would be t stat less than negative Tn minus 1 alpha. But if mu is greater than mu naught, then the rejection region is t stat greater than Tn minus 1 alpha. So this is what I mean whenever I say in this note up here. Let me clear this off a little bit. Whenever I say the rejection region follows from the alternative hypothesis, I'm just saying if this is less than, then this is going to be less than a negative. If this is greater than, then this will be greater than a positive. And if it's two-sided, it could be less than a negative or greater than a positive. So just note that this value Tn minus 1 comma alpha, this is obtained from our t-tables. This is what we were working with in the last chapter when we were looking up t-values in our tables. So maybe I should just note that, so I'll just say note divide alpha over 2 for two-sided tests. Okay. Step 4. We want to draw a conclusion. So all we're going to do is we're going to plug our t-stat into the rejection region and determine if we reject the null hypothesis or fail to reject. So if the calculated test statistic, so by that I mean t-stat, is in the rejection region, which we're calling RR, and that's determined up here, just like we were doing over here. So if t-stat is in the rejection region, then we will reject the null hypothesis and accept the alternative hypothesis. However, if the calculated test statistic is not in the rejection region, then we will fail to reject the null hypothesis. But notice we do not accept the null hypothesis. We either reject it or we fail to reject it. And then finally, step 5, our interpretation. So all we're going to do is we're going to state the conclusion, so the conclusion from step 4, within the context of the problem. And we're also going to restate our significance level. So if we reject the null hypothesis, we're going to say there is enough evidence to conclude. That's what I mean by EETC. So EETC, enough evidence to conclude. We're going to say there is enough evidence to conclude that the mean is either different, greater than, or less than. This wording would come from the alternative hypothesis. So that the mean is different from, greater than, or less than our hypothesized value mu naught at the alpha level of significance. However, if we fail to reject H naught, then we would say there is not there is not enough evidence to conclude that the mean is different than, greater than, less than mu naught at the alpha level of significance. Okay, so that was a lot. I think similar to the previous chapter, I threw a lot of information at us. It probably seems pretty weird, but once we do a couple examples, I think it's gonna become a little more concrete and less confusing.